Okay, let's try to get started. Our next talk this morning is from SERT, who's from the University of Warwick, who will tell us about projections of self-affine fractals.
Okay, so is the sound okay? Okay, all right, thank you very much. Thank you for this invitation. I'm very pleased to be in Italy and in this conference. And for this opportunity to share this work with you. So I will talk about self-affine fractals. Actually, this talk is very close to the, quite close to the mini course of last week by Wen Yupan and Jialun Li. And there is a lot of also thermodynamic formalism going into this work, but I will not get to talk about that. So, okay. But maybe the objects are slightly not mainstream for maybe audience, so I will take my time to introduce them, and please interrupt me if something is not clear, okay? And, okay, maybe before starting, I gave a mini course on that 8 months ago in Penn State, 4 hours, and I had a bunch of examples I was presenting, but actually, there was a theorem that I didn't realize, even though I gave a 4-hour mini course on a bunch of results, only after giving mini course and several talks, we realized that there is another theorem. So there is something new for even these people. Okay. Okay, so let's get started. So there will be 4 parts, and the main part is I will take quite a bit of time to introduce this Falconer's theorem. Oh yeah, so this is a joint work with my collaborator, Ian Morris, who is in Queen Mary University, everything I will say. I will talk about Falconer's theorem, and the main theorem that I will present is extension of Falconer's theorem from the year I was born to projections, okay? And then all this machinery we developed actually prior to realizing this theorem gives some new constructions strongly reducible self-affine set with exceptional projections or directions. I will tell what they are. And small sum sets with no arithmetic resonance. Maybe I will not get to talk about this. And some also new constructions, non-exact dimensional projections of some measures. Okay? Let's see what I can tell you. Okay, so let's start with the first part. So I directly start with a theorem, which is quite elementary, and which could have been proved by Banach if you give the statement to Banach, I think. So you take a complete metric space, okay? And just take a n tuple of contracting maps, okay? And okay, so given this ordered n tuple, we will refer to it as an iterated function system of contractions. Well, then there exists a unique compact set in X, which satisfies this property that it's made of its smaller images of itself, okay? So this is the compact set. I don't know how it looks, but each phi I is a contraction. So it means that k is equal to this union, phi I k's. So maybe phi 1 maps it to this part, phi 2 maps it to this part, etc. So this compact set is made up of smaller images of itself. Okay? And okay, there's a unique compact set satisfying this called we will refer to this, as the attractor of the IFS, contracting IFS. There's basically some Banach fixed point theorem applied to the set of compact sets or closed sets. But said like this, it's quite, it's just a fixed point theorem, so it's not very maybe constructive, but more constructively you can, this compact set, you can see it as the image of, there's a map. So there is n contractions, so you consider the shift on n symbols, okay, the Cantor set on n symbols. And you can cook up a map, you take an infinite sequence, and what you do is you right compose your contractions, okay, along the sequence, and you just apply it to a fixed x, okay? Now the claim is that this limit exists and it does not depend on x. So you have a well-defined, actually continuous map from the shifts from this Cantor set to x, and the image of this map, which is necessarily compact, it's continuous map, etc., is your unique compact set satisfying also. Okay? All right, so this is the set, this is the very general existence result. And so in the talk, X will be RD. Okay, complete metric space will be the Euclidean space RD with its natural Euclidean structure, and the maps will be affine maps. So let's see. So when X is RD and the contractions phi I are similarities, by similarity I understand a map of the type you take your point, you rotate it, you scale it, and you translate by a vector. In such cases, the attractor K, which is ensured to exist when alpha are strictly less than 1, it's referred to as self-similar set. Okay, there is a PAM there. It's self-similar, but also similarities. Okay. And even more generally, when instead of taking special matrices of the form rotation and scaling, if you allow your linear parts to be general affine, invertible map, so that your maps phi i's are actually affine maps, okay, the K is called a self-affine set. Okay. And already, so self-affine sets are much broader class of sets, but already class of self-similar sets, so the sets that you can construct by this construction of IFS by using similarities, contains many familiar sets that you might have heard of. Middle-Perth Cantor sets, Sierpinski triangle, Peano curve, von Koch curve, etc. So don't ask me what they are. Okay? And all right. So the question is, how does a self-affine set that I cook up in this, somehow the maps are nice, they are affine maps, okay? There's a matrix part, a translation part, the space is just RD, and there is this construction of IFS. The vague question I want to go towards is, how does a self-affine set look like, okay? Or how large it is, maybe. And okay, so, right. So these questions have by now a long history dating back to 80s, okay? And a foundational result for this self-affine set is due to Falconer, and I will take time to discuss this. Okay. So, right, maybe let me fix some notation that I will use throughout, okay? So I will fix an n. N is the number of maps that I will use. And A will always be an n tuple of matrices, A1, AN. Okay, so this is in GLD Rn. Okay. And I will take a vectors V, V1 up to Vn. This is also n tuple of matrices, n tuple of vectors in Rd. Okay. So to this data, whenever I have an n tuple of matrices and n tuple of vectors, I can associate affine maps phi I, which is phi I of x, ai x plus vi. Okay. So somehow, yeah, ti, or I denoted ti. Let me denote ti. This is the data. So, right. Remember in the first theorem, there's the contraction hypothesis, and here for affine maps to be contractions, you just need that for some norm, operator norm, the matrices are contracting, okay? And all right, so given a data like this of n tuple of matrices and n tuple of vectors, somehow I will denote this by AV, okay, to spell out some dependencies. So AV is this tuple of matrices and vectors, and associated to them is actually AV denotes this tuple of affine maps. Okay? So this is T1, Tn. And right, so once they are contractions by this first theorem, there is an associated fractal that I will denote as Kv. Okay? Well, I say it is a fractal, but it's just self-affine set. You can also construct the interval in this way. Okay, it's not the sets that you construct in this way are not necessarily fractal, whatever it means. You can also construct the interval this way. Okay, but okay, remember Kv is constructed only depending on A and V. But I somehow we will most of the time in the theorems fix A and then change V. So that's why I write Kv in this dependence. Okay. Is the setting somewhat clear? Please interrupt me. Okay, so let's go on. So Hausdorff dimension. So first of all, let me remind, as when you did in the first day of the first week, Hausdorff dimension. Okay, Hausdorff dimension is this complicated thing. So it's defined for any subset of RD. I will define for any subset of RD. What you do is you fix your delta, and you look at covers of your set by a covering of radii of sets of radii at most delta, and you sum them up, and then you take infimum of these covers, and the first S for which, so the infimum of S for which you this limit is 0 is your Hausdorff dimension. So if you vary S, you typically get something like this. Up to some S, it's 0, and there's some S0 at which you don't know what happens, and before that becomes infinity. Okay, so when you do this construction, this is the Hausdorff dimension for differentiable objects or for topological objects where you can define a reasonable dimension. This dimension turns out to be also expressed in this way, very complicated way. Okay. Good. So if you look at this definition, it's very complicated. So you need to take a delta, and especially you need to consider all possible covers. But if you look at it, it's to bound the Hausdorff dimension from above, it's somewhat simple, because if you can find a collection of delta covers, okay, say SI delta, so fixed delta and SI is a set of covers, and delta you can take to be 1 over n, such that this as lambda delta goes to 0, for some S, the diameters of these covers, as you make delta going to 0, you sum the diameters of these covers to the power S. If you can bound them uniformly, then you are good. This S that you found is an upper bound already. Okay? So to give an upper bound for your Hausdorff dimension, you only need to guess a good sequence of covers. Okay? On the other hand, to calculate or to give a lower bound is complicated because, well, you need to check that your thing works for all possible coverings. It's complicated, very complicated. Said like this, yeah. But yeah, some mathematicians are smart people, so they come up with ways to calculate this, even though it looks very complicated. Okay. Right. So, like as I said, I am now going towards explaining you Falconer's theorem. Okay. And it will include a Hausdorff notion of Hausdorff dimension, which is there. And I'm talking about matrices, so I need to use something about matrices, and I will use let me introduce some notation, singular values. So maybe this is the Hausdorff dimension, H dimension. And singular values, this is just, singular values. If you take a unit ball in RD and apply a matrix to it, it goes to an ellipsoid. And the singular values are this length of this principal axis. Okay, so I will denote them by sigma 1 of A, larger than sigma 2 of A. There are D of them. And since I'm invertible, they are all strictly positive. Okay? Equivalently, these are the square roots of eigenvalues of the A transpose time A. Okay? So these are the singular values. Just some notation. Let me go on. So let me, again, remind the setting. I'm given an A and V, a tuple of matrices, tuple of vectors. Associated to it is the affine IFS, and associated to it is the attractor. Okay? I keep it there. Right. Normally, I don't have such a big board, so And just final bit of notation. When I have a word, so remember I'm working a word in finite word, say in finite word in this alphabet. When I write AI, I will just take the usual what you can think it be. So AI is I1 up to IK, and I will take I will denote AI when it's a finite word, the product of the matrices corresponding to the letters. Okay? Just a notation. And okay, so let's now see an algorithm. I will give you a self-affine set, and let's now see an algorithm to find an upper bound, a reasonable, somewhat reasonable upper bound for the Hausdorff dimension of this self-affine set. Okay? Here is your data, A, V. This is your affine maps, contracting affine maps, and you know there exists this map KV, this set KV, and let's start the algorithm. Let's see an algorithm. So now I'll check if the dimension of the set is, so this is the argument that when you also did first day of the first week on even more complicated setting of projective space, so I will try to do it in an even simpler setting. So I first try to see if then I can find an upper bound less than 1. What do I do? Well, suppose that my contracting this compact set lies in the ball of radius 1. Doesn't matter. Okay? So, okay. Let me find a bigger chalk. Okay. Well, what I can do is that I know that when I keep applying words to this ball, it will, at the end, cover the compact set. Okay, at each level, so level 1, I will just apply the A1 up to AN separately. Okay, and maybe this goes to here, this goes to there, and this goes to there. These are all ellipsoids. Okay, maybe I should, I should not draw it like this. Okay. Here's your ball. Here's your compact set. You apply A1, maybe it goes there, A2, it goes there. Let's assume there's only 2 maps. And fine. So then what you do is you have a cover now, and now level 2, you will apply now A1, A2, all possible twofold, there is a n times n maps here. And you will get, at each level, you will get a cover with smaller and smaller radii. So I'm already getting a sequence of covers with smaller radii, which is what you needed to find the upper bound for Hausdorff dimension. And okay, so what you need to do is, well, I check what is my radii of the covers. Well, I know that this ellipsoid, one of them, has the biggest axis is sigma 1 of A, so biggest, largest singular value. So I can pretend that, okay, that these are my sequence of covers, and the diameters are bounded by sigma 1, so I just sum up sigma 1 of AI, when I is length n here, so n is 1, 2, etc. Each time these are uniformly getting close to 0. And I look at S, and I want to make sure that if I can find an S for which this sum is bounded, equivalently if this thing is, so you see if this thing is strictly negative for some S, this means this sum is bounded. If this thing is 0, this means it grows at most polynomial, sub-exponentially. It's still fine. So just believe me that if I can find an S less than 1 for which this is less than 0, then I found my upper bound. I'm happy I found an upper bound for Hausdorff dimension. Well, maybe you could not find an S for which this is less than 0, either because your set has Hausdorff dimension bigger than 1, that you cannot expect to find, or your algorithm is not efficient if it's less than 1. Okay. But anyway, keep looking. So if you cannot find an S, keep looking. Now I will be looking at the upper bound in the regime between 1 and 2. And here, I can still use this. Okay, so S between 1 and 2. But I can do the following. So let's zoom in to I take this. Here, I zoom in. Okay, so this is the radii sigma 1, which is the singular value. But I'm in the regime 1 and 2, so I can do also another thing. I know that this is sigma 2, the second singular value. I can cover this with balls of radius sigma 2. Okay? Then if I do this sum, let me just write here, versus I and 2. Now, my elements will have radius sigma 2 of AI, but I need to pay a price because I use more elements. Before, for one ellipsoid, I was using 1. I was counting it 1. But now there will be approximately sigma 1 of AI divided by sigma 2 of AI balls I will use for each ellipsoid. But if you look at that, this is sigma 1 of AI times sigma 2 of AI S minus 1, right? And S is between now 1 and 2 here. And I know that sigma 2 is at most sigma 1. So if I compare this, so if I write this as sigma 1 of AI times sigma 1 of AI S minus 1, first terms are the same. Second term, this is smaller here. So this is a more efficient covering at the scale S between 1 and 2. So I have more chances of making this convergent if it wasn't convergent for the S between 1 and 2. If the first one was not working, you see the inefficiency of your algorithm. You can upgrade your algorithm in this regime, okay? And then, well, same thing, exactly. So what I wrote here, you check if you can find an S between 1 and 2, and which will make this series converge now, okay? Sigma 1 of A, I, sigma 2 of AI, S minus 1. This is a more efficient covering at this scale. Well, same thing. If you find an S between 1 and 2, you're fine. You found an upper bound. Maybe you couldn't find for the same two reasons. And then you keep looking until the dimension D. If you find before the dimension D, you did something non-trivial. Otherwise, you say my upper bound is D. Okay? Everyone is happy. Okay. So what we did is actually, well, let's formalize a bit what we did in dimension D. For a matrix, given a matrix in GLD, I will denote phi S, so S is between 0 and D. Phi also have M to be this product of singular values. Only the last one is S minus S. So this is exactly the same thing if you take S to be a bit larger. Okay. And this is called the singular value potential, which was written in this way by Falconer, but it traces back a bit earlier to Douady, Osterle, and Kaplan-Yorke, end of 70s. Okay. And so what we did together, actually, the argument we did exactly implies that if you look at this map now, PA of S, this is called the subadditive pressure of these things, so PA of S. If you look at this, it's a map like this. So when S is 0, it's log n, because there are n maps. And it's not hard to see by Jensen, again, that it's strictly decreasing because of contraction. And it's convex between, concave between, or convex between, this is the mustache going up, convex between the integers, okay, something like that. So, okay, maybe here, and maybe let me know. Okay, so it is strictly decreasing, so it has unique 0. Again, if the unique 0 appears before D, you gain. If it appears after D, your upper bound is, you declare D. Okay? So what we did together actually implies that the unique 0 of this map, of this PA pressure, is the upper bound for the Hausdorff dimension of the attractor. Good. Not bad. And okay, so in all arguments we did, where does the translation parts appear? So you see if PA of S, you look at the definition, you see linear parts, their singular values, etc. But at the end, I found an upper bound for the Hausdorff dimension of KV, which depends on V. So where does V appear? Nowhere. Okay? And okay, so indeed, just a trivial example. If all V's are 0, this is allowed. What's your fractal? It's the singleton 0. Okay? So you did all these calculations, etc. You found the upper bound maybe, but for the set 0. Okay? For the set singleton 0. But in any case, I found an upper bound which works for every V, because they do not appear anywhere. And all right, this upper bound S0 depends only on the linear parts, as we said. It's called the affinity dimension of A. And here is Falconer's result. And okay, you fix your n tuple of contracting matrices here. Okay. Now, for every V, the dimension of KV is at most S0. This is what we proved. Okay? But the main thing of the main maybe point of Falconer's result is the following thing. If you suppose that AI is small enough, less than 1, 2, then what happens is that once you fix AIs, the matrices, for almost every translation part, so for the Lebesgue measure on RDN, you choose a typical point, you construct your system, iterated function system. Okay, A's are here, VI's are typical here. You fix in a full conal Lebesgue set. What happens is that this bound that we found is actually precisely the Hausdorff dimension. Sorry? The norm actually does, this one is Euclidean norm when you want it to be 1/2. There are some counterexamples that exactly 1/2 it's a bit mysterious to me. But. Okay, so yeah, 1/3 is due to Solomiac, but okay. So what it says is that the covering we cooked up here is for, you remember the calculation of Hausdorff dimension, you have to take an infimum over all possible coverings. Actually, for a typical Lebesgue typical V is an optimal covering. You cannot do better, you cannot beat that. This is still quite mysterious to me, but that's Falconer's result, okay? And right, and then there is at most a null measure set of V's for which this S0, as you say, always an upper bound, but the dimension of the KV can be strictly less. As, for example, when you take V to be the 0, 0, 0, 0, your KV is just singleton 0. Okay. So this foundational result of Falconer has been guiding research on fractal geometry over 3 decades. And the point is how to get rid of almost every. You see, so when I give you a fractal, these results say nothing. If I give you a precise single fractal, you will say, most likely it works, but And so what people try to do, and there was big developments after 2010 on this topic, that how to make this Lebesgue almost every in a way checkable, or can you come up with some reasonable hypotheses, algebraic, etc., to make sure that this equality holds, okay? And so this is, at least in the self-similar context, this is called the exact overlap conjecture, which says that unless some semigroup is not free, you should have equality, okay? So much more checkable, not just almost every, okay? Right. And okay, so now let's go to projections. This is in the self-similar, in the dimension 1 context, this is the theorem, this is the conjecture, which we are far from proving, even in dimension 1, all these Bernoulli convolutions and so on. But in higher dimensions, you need to be careful, but still you can come up with a conjectural statement. And actually, the main result I will present now will kind of extend the scope of this conjecture, but let's come to it later. So this is Falconer's result. Okay. So you fix your matrices, n matrices, you come up with this number S0, which is always an upper bound, whatever V you choose for the Hausdorff dimension of the attractor, and for typical V, it is exactly the dimension. Okay, now let's talk about projections. Okay, so again, I'm given an AV, and KV is attractor, and I give you a K-plane in RD, okay? And I have self-affine set here and there. I want to project my fractal on this K-plane P. What can you say about the size of K, this projection? I have a set, it's a nice set, well, fractal, but we're an image of a compact set by a Hölder map. And you project it to a plane, what can you say about its dimension? If you ask me this question 5 years ago, I will tell, okay, I know a theorem, Marstan-Mattila theorem, which tells you the following thing. If you take any Borel set in RD, and you fix a K, which is the dimension you want to project onto, well, for a typical plane now, when you project, of course, you cannot beat the dimension of K, dimension of the plane on which you are projecting. So the dimension of the projection is at a minimum of K and dimension of the set you are projecting. So just an example, if you have a 1.5 dimensional set in whatever R50, and you are projecting on a 2-dimensional space, well, almost every plane, the projection is exactly 1.5 dimension. Okay? But maybe you're unlucky that most of the dimension is seen orthogonal to the plane, and then you can lose dimension. But Marston tells you that the planes where you can lose dimension has 0 measure for the k times d minus k dimensional Lebesgue measure. So set of k planes, which is this Grassmannian, is a nice variety with dimension k d minus k, and it carries this Lebesgue measure. So this, as I said, the inequality is trivial because the projection is Lipschitz, so you cannot decrease dimension, and you can be at most k. And those planes for which the inequality is strict are called exceptional projections, and they constitute a 0 measure set for this Lebesgue measure. So if you ask me the question, if I have a KV, this fractal, and I project, I will say, well, typically you have this dimension. Okay. But what you want to do is that, okay, KV is very structured set. It comes from, you use matrices to cook it up. So maybe you can say something more. Okay. And right, so one may expect to say more than just Marston-Mattila for self-affine set. So Marston-Mattila applies for any Borel set. So you can use some more information on your set. And actually, this has not been the case. So to say more about projections of self-affine sets was not, there was not many results except for the self-similar setting. The main difference between self-similar and self-affine, maybe I should have said it before, is that self-similar setting, the contractions are all conformal. Okay, so the rotation times a scalar, whereas in the self-affine case, you see these ellipsoids with different rates of contractions in different directions. So, and this was the breakthrough results of Hochmann and Hochmann-Schmerkin in early 2010s for projections of self-similar set. And more recently, projections of self-affine sets also were studied by Baragni, Hochmann, Rappaport, and Rappaport. Again, important works. And we have some more precise understanding of exceptional projections now under some hypotheses. I will not go to there on lines and 2 planes, but nothing more. And it seems, for the moment, a bit out of reach. And these projections, you know, being a study in themselves, they are also a crucial tool, actually the decisive tool in calculating the house in going beyond this Falconer's theorem, as I told you. In Falconer theorem, you get, for almost every V, you calculate the dimension, and you want to calculate the dimension not for almost every V, but for V's which obviously do not conspire against you. And these projections are also a decisive tool, actually, to calculate, to go beyond Falconer's theorem. So in particular, towards this exact overlap conjecture in the more general self-affine setting. Okay, so fine. So let me describe the result. So it's a generalization of Falconer's theorem. It's a strict generalization of Falconer's theorem. It says the following: as Falconer, I start with a data of n tuple of matrices. So let me make a picture, actually. Maybe let me erase here. So I cannot draw so much the Grassmannian, but let's think of Grassmannian as k planes. So you take n tuple of matrices and you fix your k. K is the dimension on which you want to project to. You fix your k. It's not so important. Let's say this is the Grassmannian k RD. I will project onto k planes. And the statement says, so again, there is a finite filtration of subvarieties of Grassmannian. So this is the Grassmannian. Maybe there is a first variety here. Something, think of it as field equator. Okay? And maybe inside it there is a one-dimensional thing. Maybe inside it there is a zero-dimensional thing. Okay? There is a finite filtration of subvarieties of the Grassmannian. This white is field. And each one comes with a number, strictly decreasing. So W0 full Grassmannian comes with S0, and W1 comes with S1, etc. And actually, these WIs are stable under the algebraic group generated by AI. So they cannot be anything. Even they are algebraic varieties, but not only they are preserved by a linear algebraic group. Okay, And this is the property. So everything now is, as in Falconer, nothing depends on the translation parts. All this data that we came up now depends only on the matrices. And the following works. So for any V, you cook up your system. Whenever you fix V, you cook up your system of affine IFS. You have the KV. And now if you want to project to a point which is here, but not in the second largest one, then the dimension is at mass S0. If you want to project to a K-plane, which is in this exceptional variety, but not in the smaller one, then your projection of dimension is at most S1, et cetera, et cetera. If you want to project to this smaller one, your dimension is at most S2 for any V. Okay? And the point is that now, same as Falconer, now if you fix any P, which is, say, here in the second one, but not in the third one, okay? Then for Lebesgue, almost every V, the projection has dimension exactly this number that you found. Okay? I will talk. Then you have a trivial filtration, but even then you have a result. Okay, I will talk about it. Okay. But this is the general setting. There is no hypothesis. You just take n tuple of matrices, however they look like. You analyze their action on. You look at their how they grow. There is thermodynamic formalism in this theorem. There is finding measures of maximal dimension, so on. I will not get to that, but you find these varieties which are you can make them explicit. You find these numbers, and okay, this is what happens. Okay. Any questions? These numbers are similar to this zero of this thing. S0 is the S0, but then the other ones are calculated a bit differently. You have to go to wedge powers, and you know. Sorry? Yeah, you look at some potentials, but you look at potentials of the type. You put a projection here, Q, and you look at which you look at projections. You put projection here. You cook up these potentials, and then you need to analyze these potentials because they are not anymore subadditive, and yeah, you need to do some linear algebra and linear algebraic group theory and so on. But again, SIs are again calculated in a similar way. It's just a bit more complicated because you lose subadditivity and so on and so on. Okay. So, well, K is K equal to D is precisely Falconer theorem. When you project onto D-dimensional things, so you don't project at all, your Grassmann is a just point, so there is nothing to do. It's exactly Falconer theorem. Okay. That we... Again? N is... M is 1? Yes. Yeah. So typically when you are Zariski dense, actually, well, M is 0, but I will talk about it. It's part of the second part, actually. Okay, so the varieties VIs are explicit. They are given by levels of some pressure functions. They are G invariant. They are Schubert-type varieties, okay, so cooked up by, in the exterior products, the planes that intersect another plane in dimension at most, blah, blah. And a corollary is that's the question maybe you asked, is that if the semi-group act, so you have your matrices, A1 up to AN, all data, again, depends on these matrices, and you look at the semi-group generated, so all possible products of them, okay? If this semi-group act irreducibly on all exterior powers, and irreducible means you cannot write your matrices in a single base as a block upper triangular form, okay? And or equivalently, you do not preserve a non-trivial proper subspace. So if your semi-group acts irreducibly on all exterior powers, then the filtration is trivial, okay? And therefore, what it means, well, the first part of the theorem says nothing, I guess. It just says that the S0 we found is an upper bound. But the second part says that now wherever you project, for almost every V, the projection is exactly S0. So you kind of, you beat Marstan a bit. Now you do not look at almost every projection, but then your V's depend on the projection. So you gain a bit, but okay. Again, if the filtration is trivial, there is a new content, which is that for any direction now, for almost every V, the dimension of the projection is at most S0, is exactly S0. Okay? And similarly, if AIs are similarities, the same conclusion holds. So if, again, by the information on VIs that I'm not, these WIs that I'm not writing, if your matrices are similitudes, again, for any direction that you want to project, for almost every translation part, the dimension of the projection is exactly this S0 of Falconer. Okay, so even these two consequences seem to be new. Okay. So even when the filtration is trivial. And okay, another result, another corollary which I like is the following. You fix your n tuple of matrices, contracting enough. You fix your dimension on which you want to project. And you have this filtration. Each one comes with a number. And the following holds now. For a typical translation part, your set is, in the Marstans, you can refine Marstan in a nice way. For a typical translation part, your set is the following. For all of it, almost surely on the whole thing, dimension is S0. This is Marstan. But then there is a subvariety with its intrinsic measure. Almost surely within this subvariety, your dimension is exactly S1. Then you have a subvariety of smaller dimension. And almost surely within that, your dimension is S2, etc. Okay? It's not obvious how to, it's not in this corollary, you prove this in the following way. You choose your V's by Falconer so that the ambient dimension is S0, and then you use first part of the theorem. Because otherwise, the projections would have depend on the, so the V's would have depend on the direction of the projection, but I do not go like that. I first choose the V's, and then I use the first part of the theorem that for any V, the dimension is at most SG, okay? So don't get confused there, because I got confused. Okay, so you have a stratified Marstan type projection theorem, which means that there is a filtration of algebraic varieties. Within each one, for the intrinsic Lebesgue measure, there is a almost sure dimension. Okay, so in the same way as in Falconer theorem, which I said was guiding the research of fractal geometry for a long time, you want to get rid of almost every, you want to make it checkable. In this theorem, you can generalize this exact overlap conjecture to projections and replace almost every, there are two almost everys in this corollary, by obvious algebraic abstractions, okay? Unless the obvious algebraic abstractions happen. But this is even a more difficult conjecture than something that, first of all, this is not a conjecture because I didn't state it, but if you manage to state it, it will be even more, further. Okay, so now let me address question Bassam asked, which is the first part. So this was the main theorem. Now I will now talk about some, how much time I have? 6 minutes? 8 minutes?
10 minutes.
10 minutes, okay. Probably I will only talk about that then. Some strongly irreducible self-affine set with exceptional directions. Okay. I told you what irreducibility means, that you do not preserve a subspace, non-trivial, etc. And there is a notion called strong irreducibility. It means that your matrices do not collectively preserve a finite union of proper non-trivial subspaces. So an example here is that if you take this same group, for example, matrices, these two matrices, okay, in GL2, if you look at their action, they are irreducible. They will not preserve any subspace. But they will swap x-axis and y-axis. They will preserve the union of x and y-axis, okay? So this is a case where it's irreducible, but not strongly reducible. So strongly reducible is just a strengthening of the notion of irreducibility, which strongly reducibility means that. And in some sense, vaguely speaking, when you look at the attractor of a IFS AV, affine IFS with strongly reducible linear parts, the attractor cannot be confined in a union of fine subspaces. So in some sense, it goes in everywhere. Okay, so if your linear parts are irreducible and V's conspire, you can, in RD, you can, with this construction, you can cook your fractal to live in some smaller dimensional space. But if you are strongly reducible, somehow you, in a vague sense, you go in everywhere. Okay? And a more concrete expression of this is that actually it is expected, and also part of the path toward this conjecture, that the strong reducibility assumption on all exterior powers and a separation assumption would imply that there are no exceptional projections at all, which we are, again, a bit far from proving for the moment. And such a statement will be a decisive step to concretize the almost every V in Falconer's theorem. And on the opposite direction is that it was not known if you can cook up a self-affine set with a strongly reducible linear part, so your self-affine set is everywhere, but that possesses exceptional projections. Right? So actually, it was not even clear which hypothesis would be necessary to rule out any exceptional projections. People believe that if you are strongly reducible on every exterior powers, etc., this should be good, but it wasn't clear what is necessary. Okay? And there was no example. And actually, we will construct several classes of examples where the linear parts are strongly reducible and the filtration is non-trivial, which means you will construct several classes of fractals, KV, with strongly reducible linear part, where you have a positive dimensional subvariety of exceptional directions. Okay? So even though your fractal is everywhere, you can project it somewhere, you see a bit less dimension. Okay? The linear parts, they do not preserve anything. Okay? But, well. And therefore, for such linear parts, for almost every V, the attractor has positive dimensional subvariety of planes, or K-planes, consisting of exceptional projections. So an example is the following. If D is 2K, so in even dimension, suppose your matrices, AIs, which are in GL2K, okay, they live inside SOKK, determinant one matrices that preserve a signature KK quadratic form, and some scalings. Suppose your matrices are like this. Your ambient space is 2K square minus one dimensional. This is of course, not half dimensional or something like that subgroup, maybe a bit smaller, very nice linear algebraic group. Suppose your matrices are chosen that way, and then you have K dominated, which means that the Kth singular value and K plus one singular value, they separate with exponential speed. Okay, you can cook up such things. And it contains a non-empty open subset of H, N. Okay, so you have an open set of such things. And then there exists a K times K minus 1 over 2, which is half dimension of the K Grassmann in 2K. Subvariety such that for almost every V, this subvariety is contained in the set of exception projections. And of course, the A part is strongly reducible because I'm supposing that A is Zariski dense in H. So I did not say that. I suppose that A is Zariski dense in H, it's K dominated. So in particular, it acts strongly reducibly very nicely, but you are coming up with a half-dimensional subvariety in the K planes in R2K, for which it consists of exceptional projections. What I'm not saying, no, I'm saying that V is the new, or is a K minus K times K minus 1 over 2 dimensional subvariety. Is highly non-empty. Yes, because there can be other things. Yeah, there can be other things that I do not know. I do not expect. This would be this conjecture that I did not state. But at least there is this subvariety of exceptional projection. And similarly, you can play this game. You can take, if H is living inside GL D1 times D2, but it actually lives inside the tensor product representation of this product group, etc., you can find such things. How much time I have?
3 minutes.
Okay, maybe I stop here.
Questions for Chara?
I forgot. So, yeah, in the last example, it's nice. SOKK, you know, it acts strongly reducibly on R2K. It acts strongly reducibly on all exterior powers except for the half dimension. So if you look at wedge K, R2K, it acts irreducibly. It preserves two planes, actually. It becomes a block diagonal like this. And the example is SO11, which is the diagonal group, okay? And it is similar. And then what happens is that, right, so it happens that in the projective, let me say, you preserve some, in the Grassmann, you find like two subvarieties which are swept by the orientation and preserved, each one preserved by SONN, and somehow you play with these. It's been some time. Sorry? Yeah, for every P, which theorem?
In the one about the, hello. So it's the one you show this corollary is stratified.
No, I should not say that. That's the point. I said don't get confused about that. Yeah, I prove it differently. You can prove like that, then you get a weaker statement.
Yeah.
But I use the first part of the theorem which works for every V.
Yeah, so I wonder, can you like remove one almost every, like for almost every V, but for every P?
Yeah, that's the corollary.
Oh, that's the result?
Yeah, that's the corollary for almost every V for every P.
But okay, but I saw like 2AE in your statement, sorry.
Did I say like that?
Maybe can show
Oh, no, right. Sorry. What happens is that, yeah, you are right, I'm sorry. You're right. For almost every V, for almost every inside the subvariety, almost every V. Yeah, I guess you're right, yeah. I should have stated like that, yeah. There is one almost every there, not two. Yes, because, no, but then I cannot say that the dimension is exactly SI. I can say that for almost every V, for every P, the dimension is at most something. But if I want to have equality, so stratified Marstan, I need to say two almost every. Depends what you want to say. Sometimes you need two, sometimes one is enough.
Thank you very much for the talk. Is it possible to say in just a few words what happens with non-exact dimensional projections, or is it too complicated?
Yeah, it's a nice thing, but what happens is that as in this Ekman-Ruelle conjecture, so you, in this setting also, when you have this map, it's me right here, when you have this map from 1N, to N to RD, whose image is this coding map, okay, whose image is the fractal, any measure here, you can push it forward by this map. And what was proven is that any ergodic shift invariant measure, the image is exact dimensional for any self-affine setting. But what we construct is that we construct ergodic measures for which, and so you construct ergodic measures here, push them forward, some measures on RT, project onto some planes, they become non-exact dimensional. Okay, so this is the result that I did not state. And how to prove it? It has to do with, again, this lack of subadditivity, some limits, even though there is ergodicity, some limits you have different limits on positive dimensional sets. Yeah. Sorry, that's the most I can say. Yeah.
Okay, I think maybe we can encourage people to continue the lively discussion with Chara.
Thank you.
And we'll give him one more round of applause.